Thank you very much. This is the view that I get twice a week. It's the CERN Large Hadron Collider. They haven't actually painted this yellow thing on the ground, but this is Mont Blanc. This is Geneva Airport, which is usually where I'm headed away from or to at the time, Lake Geneva. And this is my experiment, the Atlas experiment. So I'm going to try and, it's very easy. I'm assuming, since you're all here, you're at least mildly interested in the LHC and have probably heard of it. But I'm going to, it's very easy with the LHC to go to do the wow, gee whiz, lots of superconducting magnets, lots of money, lots of people, and it's very hard sometimes to connect that with the actual science that made all these people really put that much effort into doing it and exactly how they do it. Now, I can't cover all that obviously in an hour, but I'm really going to try and, rather than wow you with how amazing it is, and it is amazing, but I'm going to actually try and explain some of it. But before I do want to say something about why the thing is so big and why we need to go to such great lengths to do the science that I'm going to describe to you. So to set the scene then, this is the CERN lab. It was set up in the 50s. I've been told, this is not first-hand evidence, that it was set up to kind of revitalize European science when a lot of European science had gone east and the rest had gone west. And it's done quite well. It's the one place in the world now where you can really do this energy frontier physics. And that hasn't been an easy path. That's been a lot of commitment from successive European governments. Many successive European governments. What we're doing at the moment is this is a 27-kilometer tunnel underground, which is full of superconducting cryogenics and very, very high-power magnets. And it's accelerating protons in opposite directions and colliding them head-on in in 4 places, actually, but in 2 that I'm going to talk about tonight. So the Atlas experiment here and the CMS experiment here are essentially, if you like, you go to all this effort to collide protons head-on. They are the cameras that tell you what happens when you collide them. This is actually about, coincidentally, the tunnel itself is the diameter of about the northern line, but the diameter of the ring, so the diameter of the ring is more like the circle line. Coincidentally, UCL built a big chunk of this, and Imperial built a big chunk of this. So this is, you can see that Kensington's a little depopulated, whereas Bloomsbury's where it's all at. There are also 2 other experiments. There's a lot more science you can do with a facility like this, ALICE and LHCb. I'm not going to talk about them all tonight, but I just want to let you know that I'm going to obviously necessarily focus on the bits of science that I'm doing at this machine. But it's a fairly general purpose facility. There's a lot you can do. And all around here is the infrastructure of what goes into injecting these protons into the thing in the first place. This dotted line here is the border between Switzerland and France. So you can see the Swiss did a smart thing. They claimed Atlas and the main kit, and then they made all the rest in France, which is good. Pleased the French farmers no end. And one of the questions, you can't do a lecture in this theatre, I think, without doing a demo. So given that this is such a high-tech experiment, one of the biggest in the world, I thought I'd have a really high-tech demo. So why is the LHC so big? Well, the thing that limits the energy that we can get the protons up to is the magnetic equivalent of the strength of this string. So if I didn't know what I was doing, this string might break and and the ball would hit one of you, or me. It's a centripetal force. It's not rocket science, right? But the difficult thing with this is not. Was that a rocket scientist in the audience? I'm sorry about that. Or maybe it was just a cliche hunter. The point is actually, surprisingly, with the LHC, it's not getting the protons up to the energy that's the tricky thing. It's actually making them come round again and hit each other. So the reason you need the big circumference and the reason you need very powerful magnets is actually to bend them. It's Newton, right? They will go in a straight line. They're very keen on going on a straight line when they're traveling at the speed with 99 point some large number of nines, the speed of light. So in order to, the trick is actually keeping this pencil-like beam, but pencil is not, it's a human hair actually, keeping it in this tunnel and making sure it hits itself head-on when it comes back. I mean, people are chuffed when they talk about the Channel Tunnel meeting in the middle. Imagine what it's like trying to make two human hairs 27 kilometers meet in the middle and collide. And the real technological limitation, and the thing that's driven a lot of technological development in this accelerator, is actually getting the powerful bending magnets up there. Okay, so, but I don't do accelerator physics. I look at the results of it, so that's all I'm going to say about that for now. The stage on which this is being played, I hope, is, yes, excellent, this. Is that working now? No, it's not. Just give me 1 second. It would be easier if this works in the end. Is this. So this is the standard model of particle physics as we know it, or most of it, which in our arrogance we would say is most of physics as we know it, in fact. And that it's most, it's not all. So what we have here is the building blocks in nature, if you like. These are the things that, as far as we know, are not made of anything else. They are just what they are. This is the electron, the neutrino that goes with it. Neutrinos aren't going to feature much in this talk, but you know that they're quite media-friendly these days. Up and down quarks are what makes up the proton and the neutron. So this is most of matter is made up of this. And then on the green side here, these bosons, these are the things that carry forces. So we know there are fundamental forces in nature. There's the electromagnetic force, which is responsible for these bright lights shining in my face. There's which is the photon, carried by the photon. There's a strong nuclear force, which is the reason the up and the down quarks stick inside the proton and the reason that protons and neutrons stick inside atomic nuclei. And then there's the weak force, which I'm going to talk quite a lot about here, which is, in a way, the least obvious force in nature. But in fact, it's the one that makes the sun work, for instance. It's involved in beta decay. It's the only one that can flip things between these generations, in fact. It can turn up and down quarks into electrons and neutrinos. So those are, as far as we know, the fundamental forces of nature. These are the fundamental particles. For some reason, these are repeated 3 times. I'm going to spend most of my time talking about electroweak symmetry breaking, as it says in the title. So I'm not going to talk about why these are repeated 3 times. LHCb, another experiment on the LHC, is doing some work on that. I would not like you... Particle physics is quite good at making big questions that we have to address, and it's correct that we do. But one should remember that they're not the only questions. And whatever we find about the Higgs is not going to tell us why there are 3 generations here, although the Higgs is, if it's there, responsible for mass, so it does tell us a difference between these, or how that happens, because these are just heavier. They seem like slightly heavier copies of the previous ones. So that's the standard model of particle physics. Now, I said that was everything, all the fundamental stuff. I'm sure many of you have spotted the absence of gravity, which would be a bit of a shame if we didn't have gravity. It's probably the first one we discovered, and it's the last one we've managed to explain, and it doesn't feature in the standard model, and it's very unlikely the LHC will tell us much about it, although it may. It's a long shot. And the other thing that's missing here is actually the Higgs boson, and which is not as obvious as gravity, I grant you, but I'm going to try and explain to you why that's important. So this is the Atlas detector. This is one of those big, I said digital cameras is the best analogy. They're there to just record. You go to all this effort to make these protons collide. You really want to know what happens when they do, and these machines are there to record everything that happens when they do. So what can I tell you about the Atlas detector? It's big. These are European standard-sized people here and there. It's kind of, I guess, if I had to say what is the Atlas detector, it's a cylindrical onion in several ways. If you see, what happens here is the beams come in here and they collide in the middle, and you'll notice there's this kind of structure, different technologies surrounding the beam. There are layers of this onion of a detector. And they collide in the middle, the beams collide in the middle here, and you've got successively different technologies doing different jobs. So right in the middle here, there's tracking detectors. So they're semiconductors. We like semiconductors because, as the name implies, they're nearly conductors. So there are a lot of electrons in there in the conduction band. It doesn't take much energy to excite them and to produce an electron and a hole. And then if you've got a voltage over that, you can read out where they were created, and then you can work out that something went by and that something happened. So, and it's very nice. We used to use things, on my previous experiment we had an ionization chamber, a drift chamber, which relied on similar principle, but it relied on electrons, charged particles hitting atoms and ionizing them and then reading them out. Trouble, to make an ion takes a lot of energy, and it would perturb the particle, so you'd measure it, but you'd have perturbed it quite a lot. With this, you get a lot of electron hole pairs very cheaply with very little energy, so it's a really nice compromise. It moves us along on the kind of measuring it without disturbing it kind of path. So we get very precise measurements here, and that's very important because some of the particles we produce decay within 100 microns of being produced, and if you can extrapolate the tracks from their decay back into the beamline and pinpoint that vertex, it gives you a lot more clues as to what's actually going on in these collisions when they collide. So that's there, and in addition to that, we have around it a solenoidal magnetic field, it's very strong, which will bend charged particles, and so of course the high energy ones are straight, the lower energy ones are bent, and we can tell the momentum from that. Which is all great, except that we know nothing about neutral particles at this stage, and there are a lot of those produced. So pi zeros, for instance, are produced hugely abundantly in these collisions. Pi zero is quark-antiquark pair, little hadron. Decays to photons, it has no charge, doesn't register at all in any of this, and there are other culprits like that. So around that we have this thing, which is a calorimeter, and again, as the name suggests, calorimeter, calories, it measures energy. It's basically very dense, it's mostly liquid argon, and it stops everything, and as the things stop, they slow down and they radiate photons as they slow down. Count the number of photons, you know the amount of energy that went in. So that measures even the neutral particles, even photons, pi zeros, neutrons will get stopped in that. And I've basically explained to you most of the Atlas detector, and I've only talked about this bit. These big wheels and all this blue stuff, and these are toroidal magnets around the edge, are all for one kind of particle, which is the muon, which is this one, the heavy version of the electron. But the muon is really special, and it's worth putting all that effort in. So what happens with the muon is, because it's a charged particle, so we do measure it here, but it's a heavy version of the electron. It doesn't feel the strong force, so it doesn't really interact with the nucleus in the atoms. It's also very heavy, so it punches through the electrons in the liquid argon, for instance, but like as though they're candy floss, it just goes straight through. So but also they're quite rare. They're often a sign that something interesting happened. If you create a muon in one of your collisions, then that's a sign that they don't appear much in nature. They appear in cosmic rays and things, but they don't appear much in nature. They're not in your average collision. So we want to know when they happen. So that's what all this effort is about. And really, it's just they punch through the calorimeter. They're just more tracking detectors, done a bit more cheaply because we can't throw all the technology that we have here on such a big space to cover them. But they measure the momentum of the muons very precisely. So that's that. And the one thing that we miss in all that, which we can't really do anything about, is neutrinos. So if you have billions of neutrinos and you build an enormous detector under a mountain somewhere, you'll see some of them. But we're going to produce them one at a time. We have just no chance of seeing them. So the only way we can see the neutrinos, that's why we have to surround the collision point, because we can only tell if we create the neutrino by the fact that we buy momentum conservation. So if we see a load of stuff going in one direction and it's not apparently balanced, then there's probably a neutrino went there. Because it could be something else, it could be dark matter, it could be something new, but we kind of know how many neutrinos to expect, and we look for anomalies there. That sounds a bit flaky maybe, but that's actually why Pauli proposed them in the first place. Beta decay is a similar situation where you have neutrinos produced and you can see something leaves the decay, but you can't see the thing. And that's why he postulated them. That's how we detect their presence, even though we don't actually see them directly. But neutrinos clearly have been seen since, and they exist. So we know how many of them there should be, and we can look for if there's more of them apparently, and then it could be something else. So that's Atlas. And that's what Atlas looked like before it was filled. These orange stripy things are those toroidal magnets on the outside. This is some guy who helped build it, who I don't know. This is from about 2005. I realized that the LHC was a bit special when I saw this in the centerfold of FHM, apparently. Not that I buy FHM, but someone said, hey, have you seen FHM? Anyway, that was in there. And it's great that people are interested, and it's great that it gets these places. Even if it does look like a James Bond villain's lair sometimes, but there we are. This is a collision event, so I show this for a few reasons. It's quite a boring event in many ways. but it gives you an idea of what's going on. First, I'd say that this event display was written by UCL, in particular by Nikos Konstantinidis, who's in the audience somewhere. There he is, good, and his students and postdocs. So that's UCL contribution. But the point of showing this picture really is that, well, first of all, you see the components in action that I was showing you before. So you see the tracks here. It's a digital representation of what we've seen of those semiconductor readouts, right? So extrapolating back to a collision vertex. This is the calorimeter around the outside. This is those big muon chambers, usually compressed to fit them into the picture. To be honest, there's nothing very interesting happening in this event. In fact, it's a sneaky event. It's the first collision event that we actually got the highest energy in the world. So this 2.36 TeV, that's 2,360 billion electron volts of energy in the collision. Now, an electron volt is the energy, kinetic energy an electron picks up by being accelerated through 1 volt of potential. So a 12-volt battery gives you 12 electron volts. This is 2,360 billion electron volts. There was a machine in the Tevatron in Chicago, which was the highest energy machine in the world, was running just under 2 TeV. And this was the moment we overtook it. It's not where we were supposed to be. We've gone higher than that now, but we were quite pleased to overtake it. What's even more funny is that we weren't supposed to have this event. The LHC were doing some tests, and they didn't tell us they were doing this, but we guessed. And some of our students and some of the people involved in it were in there, and the detector was turned on. We were desperately looking at these events. You can tell it's a cheat because I said there was a magnetic field, and none of those tracks are bent. We didn't turn the magnetic field on even. We weren't ready, really. But we thought, well, I'll just take an event anyway. So that was it. That was the first event. This is much more typical of what we see now. This is at 7 TeV, which is a factor of 5 bigger than what we saw before. What's happening is that the beams are colliding in the plane. In this represents, there are 3 pictures of the same event. In this picture, the beams are colliding in the plane of the board, in the plane of the screen. And you see this stuff throwing off, which I'll explain in a minute. In this picture, the beam is along here, and the one proton comes in there, and they collide, and stuff flies out. And here it's like if you kind of split the cylinder and rolled it, laid it flat. And these towers here are the amount of energy in these clumps that you see, these yellow blobs in the calorimeters that are measuring. So it's a way of us getting some idea of what's going on. What you're seeing here is that we've collided 2 protons together. Now, we don't really collide protons at the LHC because the energies are so high. The proton is such an enormous thing on the scale of things you can see at our energies that really we're colliding gluons and quarks together. The proton is made up of gluons and quarks. And we collide gluons and quarks together. And they hit each other and they bounce off and they head off, and you would expect to see them maybe. Gluons and quarks don't actually appear in the detector. And this is because the strong nuclear force is a force, electromagnetism, as you pull 2 opposite charges away, the force goes down, gets weaker. In the strong nuclear force, it's more like an elastic band. The force gets stronger as you pull them apart. So inside the proton, they behave like the free until they get to the edge of the proton kind of thing. And as they fly away from each other, there's a huge potential energy builds up between them. And as that happens, then it becomes at some point energetically more favorable to create more quarks and to have, instead of quarks free, to have 2 hadrons flying away from each other instead. There's an equation that explains that. I'll show it in a minute. But you just imagine this huge potential energy in the elastic band, and suddenly the band snaps, if you like, and the quarks and gluons are the ends of the band. So what you end up with is a spray of these hadrons made of quarks and gluons, and that's what all these tracks are here. There's a whole, but the direction that the average energy of these things goes in is the direction that the original quark or the gluon went in, and these are called jets. So we reconstruct them that way. So that's what we're doing at the moment. We can produce other things other than just scatter quarks and gluons, and I'll say something about those in a minute. But this is a kind of typical-ish interesting event that we see. And in fact, we're now colliding many protons together at the same time. So these are n different proton, I don't know, but 9 in this event. Different sets of protons collided. It's all happening on a kind of 50 nanosecond timescale. We've got to try and unpick what happened in all this. 50 nanoseconds is interesting. Speed of light is about 1 foot per nanosecond, right? If I'm allowed to use feet as a unit. So 50 nanoseconds, the experiment is bigger than 50 feet, right? So we've got one event coming while the other one's still leaving it. And that's even in the bunch crossings. But within every bunch crossing, we've got many events as well. So there's a lot of, this is why the detectors have to be very precise and where the computing challenges are just ridiculous to actually work out what goes on in these collisions. But what happened in this one is basically these are all boring. And this one's interesting because it's got 2 muons in it. This is actually a Z boson, one of the carriers of the weak force, that was produced in that collision and decayed to 2 muons. And this is why we put a lot of effort into these muon detectors, because that's how we pick out this kind of stuff from this kind of stuff. So we were interested in everything at some level, but we have a lot of examples of these ones and very much fewer of these. So we're interested in those kind of events. And a lot of the art of this stuff is actually going through this massive data that the LHC can produce and finding out what you can learn from it. Of course, it's science, that's what you do. But we have it coming in at kind of 9 events every 50 nanoseconds or something. We have to kind of do some of that online and make sure that by doing it in our electronics, we're not missing something that we would wish we'd saved. If you build your trigger, it's called the trigger, this thing that makes sure you save the right events. If you build your trigger electronics and everything perfectly, so you only save what you want to save, if you do it wrong, you will only ever see what you expected to see, and there's no point doing the experiment in that case. So you have to keep your eyes open. These are our electronic eyes. Okay, I said I'd show an equation that explained that quark thing. This is it. So we have a lot of energy in this potential between the quarks that allows us to create new quarks according to E equals mc squared. If you have enough E, then even though c squared is a big number, you can make new stuff. And that tells you also why it's one of the reasons. I'm going to go now through 3 reasons why it's interesting doing energy frontier physics in general. So one of them is this, that if there's new stuff out there, there are new fundamental degrees of freedom in nature, there are new particles, for instance, the Higgs boson, but maybe other stuff. If you want to see them, you have this potential well to climb. You have to create them. So if you want to create a new particle with some mass, you need c squared times that mass energy in order to create it and see it. So at some level, we're just exploring, right? We know that the universe has very high energy areas in it. We know that the physics of this high energy impacts on our understanding of the universe. This is just a way of looking. We're kind of looking under stones, if you like, to see what's there. This is a frontier of nature. There are other frontiers, but this is one of them for sure. Okay, so that's one reason why we want high energies. Another reason why we want high energies, I think this is where you get my bad cartoon. Yes, excellent. So I keep thinking I might upgrade this, but I never do. The way I prefer, actually, than the E equals mc squared is to think about this. This is my preferred justification for the kind of science I'm doing, is that we want to study nature at the shortest distances. We want to look and look. There's a long history of looking, down from matter to see what it's made of, to atoms, to see what's inside the atom, to see what's inside the nucleus, to see what's inside the proton and the neutron. And it's been a very fruitful field of endeavor. And in order to look at very short distances, you need very short wavelengths. So this is why, if you like, one of the reasons we see in the optical wavelengths at hundreds of nanometers, because if we used, for instance, radar to see, then it would be useless. Radar is great for seeing a ship or a plane because it's got wavelengths of a meter, but if you want to see a doorway or your friend, then it's not going to be much use. Optical frequencies are much better for that, and they can go a lot more fine than that. If you want to start studying surface science and really looking at the details or looking at proteins or something, you need things like X-rays or electron microscopes or something because they've got much shorter wavelengths. We don't even want to do that. We want to look right inside the proton. We want to maybe even look inside the quark and see what's going on. So we need the shortest wavelengths ever produced anywhere in any experiment. So that's fine, but the trouble I always get here is without doing quantum mechanics, how do you know that wavelength has got anything to do with energy? And the best analogy I've got, so those of you who are physicists or chemists will know that blue light is higher energy. Blue photons are higher energy than red photons because they have a shorter wavelength. But the classical analogy that I always pick is the double bass string. So if you have a double bass string, or a bass guitar string, Charlie, is that all right? Yes, my bass player over there. Bass guitar, a bass string, right? A big fat string. And you pluck a note, then of course you get a deep note. It's quite easy to make a noise with it. If you half the string length, you get an octave higher. And it's actually a little harder to get a note out of it. If you imagine taking a big fat bass string, making it, say, 2 centimeters long and trying to excite the vibration in that and make a note, you'd have to hit it extremely hard, right? You have to put a lot more energy in to excite any kind of vibration in that string that you could ever hear. That's a classical analogy, but it actually is it's a very good analogy for what's going on in quantum mechanics. To excite short wavelength things, you need huge amounts of energy. So that's why we need the energy. We want to study nature. We want to look inside the quark, see what's going on there. The third justification, which is probably my least favourite because it's kind of historical, but given where I am, I should go with it. It's the energy density of the universe. You hear the LHC described as the Big Bang machine, which was a bit embarrassing when it broke the first when we. But you also see that you hear that we're recreating the conditions of the first just after the Big Bang and stuff. Well, of course, we're not really, right? I mean, the universe had all the energy in one place then, and we don't have all the energy in Geneva. Believe me, you would know that if you've been out in Geneva. But what we do know is that this is the physicist universe, right? This is a spherical cow or whatever. This is the universe now, represented in less dimensions, of course. And we know it's expanding, and we know there's a certain amount of energy in it. So we know that in the past it was smaller, and there was the same amount of energy in it. So as you go backwards, everything is getting more energy, more dense. The energy is getting more dense. Energy density is basically temperature. Everything's moving faster. All the particles in the universe are moving faster. They're bouncing off each other faster. And so there's this really high energy density. At some point, things are bouncing off each other so fast, atoms are bouncing off each other so fast, they cannot remain atoms. They ionize, it becomes a plasma. The electrons are just knocked off in just your average collision. That's fine, we can do that in labs, we know that happens, that must have happened then. At some point, even the nucleus doesn't stick together. Protons and neutrons can't hang together because they're getting hit off each other so much. And at some point, even protons and neutrons don't hang together, and you have quarks and gluons all the time. And you go back and back, and you say, well, do we understand the physics of this stage, of this stage, of this stage? At some point, there will be a point in this regression back to the Big Bang where every particle, every quark or gluon, which is what would be around then, would be colliding at the typical energy. The typical energy of a collision would be the typical energy of a collision at the LHC. So we're taking a very few, very lucky quarks and gluons and banging them together with the energies that every single quark and gluon would have been experiencing in a few micro, but 10 to the minus 34, actually, I think, after the Big Bang in the end. Seconds after the Big Bang. So, well, it's between 10 to the minus 34 and 10 to the minus 12, I think. I got a little paranoid about this because I don't know if I was on Horizon lately and I got the age of the dinosaurs wrong by 3 orders of magnitude. So now I really don't want I really don't want to get the age of the W and the Z boson wrong by the same amount. But it's something like, it was between 10 to the minus 34 and 10 to the minus 18, I think, is kind of where we're probing at the LHC. So in a sense, there is some truth in this, that we are actually looking at the physics, which is at the moment unusual, though fundamental physics, but it was the only physics at that time after the Big Bang, and it clearly has something to say about how the universe evolved to where it is now. And this is the picture I got just to remind me. So they're 10 to the minus 34. You can see here, this is us, apparently. This is where the atoms break up. This is where the quarks and gluons break, the protons and neutrons break up. And this bit where the W's and Z's appear is where the LHC is probing. Beyond that, the cosmologists think they can say something about some of it. No, they don't, actually. The cosmic microwave background is about here. And we don't really understand the physics back of that, although there are cosmological theories that at least have some plausible explanation. But this is where we're actually doing the science now. So yeah, 10 to the minus 34, 10 to the minus 10, I was okay. There's 3 orders of magnitude between friends anyway when you're talking about 10 to the minus 34. Okay. So that's why we built the thing. That's why we went to all this effort. I'm now going to try and explain. And I've also told you something about how we detect what went on, right? In the semiconductors and the magnetic fields and things, the calorimeter. I want to now try and tell you the kind of plots that we're poring over every day, trying to see if we can see something in them and what it means when we say we see something in these plots. So to do that, I start with a Feynman diagram. This is actually a sneakily disguised equation. Because Feynman diagrams are absolutely beautiful in that they map on completely to the quantum field theory. They're much easier to understand. They're so easy to understand that actually a lot of physicists only understand the world in terms of Feynman diagrams, and they sometimes take that a little bit too far. But I get told I meant to do this. I got told off today when I showed this to some students. I should draw my time axis on this. Time is going in this direction. So what you have here is an anti-electron, a positron, meeting an electron. They annihilate. There's a photon produced, and then they decay again to the same thing again. Okay, this is what actually was going on in the tunnel that the LHC is in now, but there was a machine called LEP in there, which is colliding electrons and anti-electrons. Before that, it shut down in the year 2000, so we could build the LHC. So I'm going to talk a little bit about what we learned from that. But one of the things that's interesting in this is, if you remember that equation, yes, that equation, E equals mc squared, and then remember energy conservation. And there's a problem here. So the energy has to be conserved. So the energy here has to be the same as the energy here, has to be the same as the energy here, okay? Now, we collided this electron and positron at horrendous energies. 90 GeV it was when LEP turned on. So 90 GeV here, 90 GeV here, 90 GeV here. There's a problem. The photon has no mass. So how can the energy be 90 GeV if m is 0? E equals mc squared. If this is 0, what's going on? So the concept that we have here is this concept of virtual particles. And this is kind of a technical concept, but important concept that I want to get across. So we said the forces are carried by particles, okay? They're carried by the exchange of these particles is what mediates forces. The thing that is, though, in quantum mechanics, all you ever measure, it's like Young's slit experiment or something, you can't measure which slit the thing went through without destroying the effect. All you can measure is where you started from, where you ended up, and everything in between is just a way of calculating what might have happened. And these particles, this photon, is a way of calculating what might have happened. This is actually what I mean when I say physicists sometimes take these things too seriously, because there's often no physically well-defined way of saying, did this Feynman diagram occur or this one? Often they both might have done. It's quantum mechanics. You don't know. All you know is if you put all the right ones together, you'll get the right answer. So these are virtual particles. The forces are carried by them. They don't have to have the correct mass, is the thing. That photon does not have to have zero mass. So this is a way of, you can derive this from quantum field theory. You can actually derive Heisenberg's uncertainty principle from quantum field theory, but it's good to think of this as a manifestation of that, if you like. And that this thing is more likely to happen if that photon can have the correct mass. And as it moves away from the correct mass, it becomes increasingly less likely to happen, or decreasingly likely to happen. And the formula that governs that is actually this. It's not that tricky a formula. This q squared, the q squared there, is the mass it has to have in order to conserve energy via E equals mc squared. The m is the mass it really ought to have if it's a proper photon, which is 0, actually, in this case. But I'm going to show other ones that are not 0 in a minute. So, and this is 1 over that. So when those are close together, the way I've written it would be infinity. Now, it's not quite infinity, but you'll see a huge spike. It gets very large. And as you move away from it, the probability of that happening drops. So for the photon, in this case, the energy is 91 GeV. This is one of those collisions at LEP. The mass, what does it have to be? Well, it has to be 91 GeV over c squared. And so why did we do that? Well, the reason we did that is there's another particle there. There's the Z boson, which is one of these carriers of the weak force, which has a mass of 91 GeV over c squared. And so what you should see, if you say tune up, if you collide electrons and positrons at higher and higher and higher energies, you should see the probability of this happening, of them colliding and annihilating like that, and having something in between, falling as you move away from the photon. But then as you get near the Z, that 1 over q squared minus m squared would start getting bigger again for the Z, and you would see it go up again. And that's indeed what you see. This is the data. These are the data. This is the total cross-section, which, if you're not familiar with cross-section, you can just think of the number of times it happens, or the event rate, the probability, if you like, of it happening. And you see this is the mass of the particle that has to be in the middle, or the center of mass energy of the thing. And as you move away from the photon, which is a 0 mass, it drops and drops and drops and drops, and then it rises up again, and this is 90 GeV. This is where the Z is. This bump is that 1 over q squared minus m squared bump. It's not quite infinite, as I said. There are other terms that come in, but it's very large. It's you wouldn't miss this, right? This is not so esoteric. I have to say, I'll show you in a minute. I just find this remarkable. It's such an unnatural-looking shape for something to happen like that, but it does. And you see also there are things like, so this is when it decays to hadrons to quarks. This is when it decays to muons, same thing. This curve that doesn't have the bump in is when the E plus E minus give you 2 photons, and the Z doesn't have any charge, so it doesn't couple to photons. There's no diagram you can draw that has 2 photons and a Z in it like that. So there's no bump. So we really know what's going on there. We can also see it at Atlas. So this is data from the LHC now. This bump here is the same bump. There are several things to notice here. First of all, I said we're really colliding quarks and gluons, and you may be surprised to know that the proton has antiquarks in it as well. It does. It's got three, at its most basic, it's three quarks, but they're swapping gluons. In quantum mechanics, they're swapping gluons between each other all the time, and there are quark-antiquark pairs in there. So you can collide antiquarks and quarks at the LHC. They can annihilate, they can give you a Z or a photon, and it can decay to E plus E minus, and this is one of those, a measurement of that. This is the Z bump. And one of the things to notice here, one of the things to notice here is that the energy reach is much, much higher than this, right? This kind of dies away about the Z. The later experiments went a little higher, but this goes really high. And this is one of those plots we're frantically looking at all the time to see if another bump shows up. Have we got another Z? Have we got something else going on? So far not. These are some people's dreams as to what might happen. They're always just a bit beyond where the data stops, but it's the way it goes. But this is an example of kind of this scan above at high energies, what you're looking for when you might see something new. When we say we're looking for physics beyond the standard model, we don't expect any bumps in this, but we'd love to see one. So back to the standard model then. This is the diagram, the thing I showed before, the kind of little zoo of particles, is up and down quark, the electron, the neutrino, and the heavier partners, and then the force carriers, neglecting gravity. So the whole point of what I'm going to try and tell you now is why not just looking above in that. Of course, it will be interesting to look for new physics at higher energies than anyone's ever looked before. We're looking at the universe around us so carefully. So we're breaking new ground. It's a frontier of knowledge. Of course it will, but is it really, really worth all this effort? These scientists, 6,000 of them or whatever, could have been doing other science. Why is this the most important question to ask? What I want to try and tell you now is that there's a really special. We're not just looking into new territory. We know there's a question that is really important that we will be able to answer. Now, those of you who are researchers know that is a really precious thing, a well-framed question that you can get an answer to. Not a lot of good science, a lot of good science doesn't come that way. A lot of good science is serendipitous, that you did something you didn't think was going to be interesting, and it turned out it was the most interesting thing you ever did. But if you're going to invest this much of your career and this much money, you want to know at least you've advanced knowledge at the end of it. You can't just do it on spec. And I'm going to try and explain to you why the energy reach of the LHC is really special in that sense now. And it's connected with these guys, with the photon and the Z and the W. Now, there are two forces, the weak force and the electromagnetic force. And this is another one of these scattering cross-section plots, like the LEP one that I showed you with the bumping. This comes from an experiment in Hamburg that I did my PhD on, in fact. And what this experiment did was collided protons and electrons together, which is, they don't annihilate, they're completely different particles. It's almost like a big electron microscope studying the inside of the proton, and it did a lot of that. It really taught us a lot about how. One of the reasons we can do science at the LHC with confidence now is that we understand how quarks and gluons are distributed inside the proton. So what you have here, you've got a blue line and a red line. Ignore all this stuff down here for now, just look at these. What on the axis here is the rate, the probability, the event rate, if you like, of what happens, and it's a logarithmic scale, so it's different from the one before. It's really going up very quickly. And everyday energies are down here, and this is what happens when you bounce an electron off a proton, and it bounces off and you see an electron bounce off, which is kind of what you'd expect. Okay? And at everyday energies, that happens a lot. That's the dominant thing. As you go up in energy, it drops. And the reason for that, we know now, because the photon you exchange has to carry a huge amount of energy. And as it carries more energy, its mass has to go further and further away from where its mass ought to be. So it becomes more and more virtual, less and less likely to happen, and it drops on a logarithmic scale. It drops very quickly, okay? The interesting thing, or the other interesting thing on this plot, though, is this red line. The red line is the weak force, and that's when you bounce a proton, an electron off a proton, and you don't get an electron back. You don't see an electron bounce off. What you see, or don't see rather, is a neutrino. So what's happened there is instead of swapping a photon in this diagram, you swapped a W boson, which is one of the weak force carriers. And the W boson is charged, so it carries the charge of the electron. It turns the electron into a neutrino. Now, we don't actually see the neutrino, as I explained on Atlas, but we can tell that it was there because we see the quark that the electron bounced off fly off in the other direction. And we know something must have gone in this other way. Otherwise, we've given up on momentum conservation. So, as I said, Pauli decided that it was neutrinos rather than momentum conservation that had to go a long time before. So we can measure this process, charge current, it's called, interactions, where a W is exchanged. It's a weak force. So we have the weak force and the electromagnetic force. And you'll notice, though, that as you go up in energy, this is everyday life, if you like, down here. as you go up and up in energy, the weak force isn't falling very quickly, if at all at first. And the reason for that is that the W, even in everyday life, is a long way from its mass. The W wants to have a mass of 80 GeV. In everyday life, we have nowhere near enough energy to make any W's that are anywhere close. So it's very unlikely to happen. That's why it's called the weak force, it turns out. The weak force doesn't happen very often because the W and the Z are heavy. And the electromagnetism happens more because the photon is light. But that's not a pun, actually. The photon isn't as heavy. So as they go up in energy here, you see that they come together. And this is the electroweak unification scale, if you like, or I prefer to call it the electroweak symmetry breaking scale because I think backwards. So what's going on is that there's a symmetry between these forces up here. They've got roughly the same strength. They're qualitatively very similar objects. And at some level, as you go down in energy, that symmetry is broken, and they break apart. And you have a completely different weak force from electromagnetic force now. But in the early universe, or at the LHC, they're the same, or they're very similar anyway. There are differences, but they're mixed up together in that way. So this is this point, electroweak unification here. This is a special scale in nature. And the important thing to point out is that this is not theory. I mean, the lines on there are theory, but the points are data. We know this happens. This is not a fantasy of some particle physicist. There's a special energy scale in nature which we're doing physics above for the first time at the LHC. And we want to know why how this symmetry is broken. We know it's broken by the mass, in fact, but we want to know where that mass comes from. What's the mechanism? What's going on there? Now, electroweak symmetry breaking is a really fundamental concept, and it appears in a lot of physics. And in fact, Peter Higgs, whose name is on the Higgs boson and who first proposed this, the mechanism that we think is behind this at the moment, got a lot of his inspiration from condensed matter physics, where this stuff happens. So I have two fancy demonstrations. Hi. So one of them is pretty low-tech, and I will do this while we get ready for the first one. So, although the low-tech one might be more dangerous, amazingly, given what happened earlier. But so this is the wine bottle. The answer to the universe is in this wine bottle. I don't know if you can see it. I should bring it in front of the screen. So there's a wooden marble in the wine bottle. It's quite important that it's not glass. This is the everyday universe. It's an empty wine bottle with a marble in the bottom. If you imagine going back in time or going up to higher energies, then you shake the bottle up. The marble can be anywhere around the axis of the bottle. But as it cools down, it has to choose, okay? So the idea is that there's a completely symmetric situation. There's a complete symmetry around the center of the axis down the middle of the bottle. No preferred direction. If I shake it again, the marble will come down in a different direction. Won't you, marble? Yes, there you go. So, okay. So what you have here is a symmetry in nature, which is the symmetry around the middle of the bottle, which is not broken by gravity. There's nothing to break it, really. But because of the bump in the bottom of the bottle there, as the bottle cools down, as the marble loses its energy, loses the kinetic energy that I give it by shaking it, it has to choose. It has to break the symmetry. And now this is no longer a symmetric situation. There's a special direction. The marble is on one side. That's the analogy of what's going on in the Higgs mechanism, okay? But there's a much better and closer physical analogy to this, which we'll show you in a minute. But there's a diagram of it here, which is in a magnet, which we've got here. It's niobium, is that right? Neodymium, sorry. Need a condensed matter physicist, sorry. We're going to heat this up. This is something that is a magnet, okay, at the moment. If we heat it up, it stops being a magnet. So you see that at the moment it's a magnet. This is the magnetic sensor showing it as a field. Now we heat it up, and we just have the slide back while he heats it up again for a minute. So when it's heated up, we're going to go to this situation. All the little magnetic dipoles in the material are jigging around because of the heat, and there's no preferred direction. And Maxwell's equations, thanks to Faraday, we know that they're symmetric. There's no special direction in nature. I mean, there is on the Earth. There's North and South Pole, but we know why that is. But there's no real special direction. The whole of Maxwell's equations are completely spherical symmetric. And these are just doing that under Maxwell's equations. But as they cool down, a couple of them will notice that they have slightly lower energy if they line up together. And as the temperature goes down, there will no longer be enough energy to move them away again, so they'll stay there. And then two of them are aligned, another one will align. And in the end, they will choose a direction, and they will all line up together, and you will end up with a magnet. And that's what's going on here. So this magnet we've heated up will, hopefully, if this works, become non-magnetic. The magnetic field's gone, right? So, no, it's not moving. So, and that's because we've jiggled all those little dipoles that were lined up. They've been heated up. They've all jiggled around. That's the analogy of the early universe, or the LHC, if you like, going to higher energies where this symmetry is restored. There's now no special direction. There's no magnetic dipole going on in this thing. There's a complete symmetry. As it cools down, we don't put it near anything fancy, and this will come back. If we just leave it to one side for a minute. So what I haven't done is explained why this idea of symmetry breaking is important, and that is rather difficult to do, why we think there's some symmetry. So you can see there's some symmetry here. I mean, really what I've told you is the forces look the same. That is a symmetry. But if you just kind of break it by hand and put in the mass of the W and the Z, the whole theory falls apart. This has sort of been Nobel Prizes awarded for proving this, that you cannot have a predictive quantum field theory without this symmetry being built into the theory. Yet we know in nature this symmetry isn't there. So this whole business of spontaneously broken symmetry is a dodge to get around that. It's a way of saying, yeah, the wine bottle's symmetric, gravity's symmetric, the whole potential is symmetric, but the ground state, when I leave the wine bottle alone, is not symmetric anymore. And we're in the ground state, we're in the low energy state. Fundamentally symmetric forces lead to a fundamentally asymmetric ground state. And it looks like, as we cool down again, we've retreated, the magnetic fields come back again, see? So it won't be in the same direction that it was before necessarily. It's just they've chosen another direction and they've said, OK, the atoms were all lined up. We jiggled them around so they weren't, which is the analogy of the early universe. As they cool down again, they pass the Curie temperature and they all line up again. So spontaneously broken symmetry is actually, crystallization is also a spontaneously broken symmetry. You have a completely symmetric liquid. As you cool it down, it will crystallize and suddenly chooses special directions, crystalline directions. So it's a very common feature in nature, and we think, based on that, thank you very much. We think based on our, I didn't believe they could do that, it was great. We think based on our mathematics that this idea of spontaneously broken symmetry, we know it's an emergent phenomenon. It happens, we just saw it happen twice with the bottle, maybe less convincing, but with that, it's pretty good. We know it happens in nature in collective phenomena. It seems that it might be really fundamentally behind what's going on. Why mass is there at all? Not just how does collective systems of matter behave, but why they have mass in the first place. And that's the Higgs boson. So the postulate is that, and I gave a talk similar to this to some students, A-level students today, and the question at the end of it, isn't this a bit like the ether? And it's true, it is. The Higgs field fills the universe. It's responsible for it's the bottom of the wine bottle. It's the Higgs potential. It fills the universe and it gives everything mass, and all the maths works out. How do you satisfy yourself this is really true? Well, you go look for experimental evidence, and the only way to detect a field that fills the whole universe is to excite that field, excite a wave in that field, if you like, vibrate the field. So, I mean, you can imagine if you didn't believe that there was any air in this lecture theatre, for instance, how would one piece of evidence that tells you that there is actually some air in here is that you can hear me. There are sound waves travelling from me to you. That if you lived without the material to detect air, one way of detecting it would be to shake it, to make a noise, and say, OK, there are waves travelling across this thing, very like the ether, right? We thought there was waves. We thought there was something that electromagnetism had to travel in. It turns out it's the electromagnetic field, not the ether. But nevertheless, the way of detecting an electromagnetic field, if it's just constant everywhere, there's no way of detecting it. You have to excite an electromagnetic wave. You have to have a photon that shows you. The Higgs boson is the reason. Is the experimental, that would be, if it exists, will be the experimental evidence that this field is there. So if something's everywhere, it's very hard to detect. You need a lot of energy to excite a field. Now think about the double bass string again. We need a lot of energy to excite a vibration in it. What we're trying to do is excite vibrations in this field that fills the whole universe, the Higgs field. And those vibrations are the Higgs boson. So in the quantum mechanics, waves and particles are pretty much the same thing. So this particle, the Higgs particle, the Higgs boson, is basically a vibration in the Higgs field that is the bottom of the wine bottle. It's the thing that breaks this symmetry and gives the W and the Z mass and doesn't give the photon mass, because that's what the ground state of nature is as you come down. But it's the ideas, we know these ideas work in everyday physics. What's fascinating now is that they might actually be very deeply, fundamentally built into the nature of the universe, even at the smallest scales we can look at it. So that's the kind of grand scale view of what we're doing. I want to, to be honest, any competent LHC physicist could have given the talk I've just given you. There are 3,000 people working on my experiment. We're not daft. We put a lot of time into this, a lot of effort. We know why we're doing it, and this is one of the main reasons why. It's not the only one, but it's one of the main reasons why. I want to take a little detour just to show you something that I've done myself with my student, just for fun, which is related to this as well. So what we have here is something, again, I'm trying to give you an idea of how you really do science with this. I'm trying to connect the gee whiz stuff with the actual data, with what you actually do day to day. So this is one of the ways a standard model Higgs might appear in Atlas. So this would be a quark, and it should be an antiquark annihilating here. It'd give you a Z boson. Z boson is very heavy, so it's actually relatively likely to kick off a Higgs. There's a number associated with this vertex here, which is quite large. It's to do with the mass of the Z. So it's quite likely to happen. So you can get, this is one of the ways we might be making Higgs bosons right now. Well, not now because we stopped for Christmas still, but until December and starting up again in March, making Higgs bosons at the Large Hadron Collider. There's a problem with finding these, though, because the Higgs is, it's responsible for mass. So the heavier something is, the more likely the Higgs is to decay into it, which is sensible, logical. It's one of the things we need to, that's kind of fingerprint of the Higgs. We need to see that, actually. But the problem is, for the range of mass where the Higgs might be now, as we know now, we didn't know before, but we do now, then the thing it's most likely to decay into is a pair of quarks. It's the B quark, the beauty quark, or the bottom quark, depending how romantic you are. To BB bar pair, because it's the top quark is the heaviest quark, but it's so heavy the Higgs can't decay to it, but the B quark it can decay to. So it will do, and the problem with that is that, as I showed you here, we got quarks all over the place at the LHC, and quarks don't show up as beautiful little objects that you can tag in the detector. They're mixed up with gluons. There are lots of up quarks, down quarks, strange quarks, charm quarks. It's very hard to find them, pick them out. So it's not, we might be creating Higgses and just missing them because they're decaying to stuff that we can't pick out. It's a needle in a haystack, but the needle's kind of straw-coloured and bendy. It's not really working. So we have trouble with that. Now, that's a little pessimistic because the B quarks are a little special in that they do decay in the end to something else. But in the end is maybe 100 microns from when they were created. And so there is a way of maybe detecting that there was a B quark in there. That's why we had that precision silicon detector that I mentioned before. For instance, you can see that not all your particles came from the same place. Some of them came from a few hundred microns away. That's the signature that maybe a B quark was there. So there is information we can extract. But even given that, there are a lot of B quarks created just from gluons colliding. So there's a huge background to this. So the Z is useful. This helps us pick it out. If the Z decays to muons, that's also useful. It's a sign something interesting happened. But even given that, Zs plus gluons, which go to B quarks, was a killer. So people had kind of given up on this. So in 1999, which was roughly when I joined the experiment, actually, where we were preparing the experiment, the studies had said this is probably not worth looking for. Okay, there are other ways we can find the Higgs at the LHC, and I'll talk about them in a moment. But this is probably not worth looking for, because you'll never pick it out from the background. So we had an idea, this is me and my student at UCL, and there's a friend of mine who's a theorist in Paris, and his student. So, well, okay, we'll give up on most of those events, but what about, we have so much energy at the LHC that sometimes the Higgs is moving really quickly. And then instead of having one jet of stuff with a B in it and another jet of stuff with an anti-B in it, you have them both together, and they're both inside. So all that stuff is inside this jet. And that's probably why we're missing a lot of these golden events. They're the kind of highest energy events. They should be the easiest ones to see. But everything is stuck inside this mess here. And we're just missing it because of that. So we came up with an idea of how you can interrogate that mess and find out that there were two Bs in there and that maybe they came from a Higgs. And so to cut to the chase, this is a simulation plot of that. And again, another reason for showing this, apart from kind of vanity, because it's one of my own plots and I want to give you some kind of personal view on the LHC rather than just the generic LHC talk. But also, this bump here is one you've seen many times before. This is unfortunately not real data, but it might be in a few years. And this is simulation, but this green bump here is one you've seen before. It's about 90 GeV. It's the Z boson decaying to a B and an anti-B in exactly that kind of diagram. So you can have this diagram, instead of a Higgs here, you can have other things going on, and you can have two Zs or a W and a Z coming off. So that's there, and it should be there. We know that that exists, so we better see it. If this technique works at all, we'll see it. But this blue bump is what a Higgs would look like if it had 120 GeV mass, and you see that it shows up really quite well. And this is now one of the techniques that we're using to look for the LHC that was developed at UCL, and we're quite proud of it. So it was a bit of a vanity detour, but I wanted to show you something that was me rather than just the whole LHC. This is what the whole LHC is doing. This is what we're doing right now. That channel with the B and the B bar, it's very nice. It's a great thing to look at, but it's not going to be the first place we see it if it exists. First place we see it, bizarrely, is if it couples to photons, which is a bit weird because photons don't have any mass, but they're easy to spot. And the way it couples to photons, it has a little loop via a top quark, so don't need to worry about it. But we might see it. This bump here is what a lot of the excitement was about in December. It might be that in this spectrum that there's a little bump there, which is the sign of a Higgs at about 120 GeV going to photons. This bump here is a simulation of a Higgs at 130 GeV, but this one obviously isn't there. If it's there at all, it's about 126. So we're looking for photons that may be produced from the Higgs. We're also looking for Zs that can come from the Higgs, and the Zs go to leptons, and it's a very clean channel. And it doesn't happen very often, but if there's a Higgs at about 125 GeV, you should see a few more events here than you expect. And indeed we do. Not many. You can see the size of the error bars there. I wouldn't take this to the bank. This is why we're not saying we've discovered it. But it's suggestive, and you can churn this through your statistical analysis and see what it tells you, and this is the kind of limit plot that we make. So this is the Higgs mass along the bottom here. This dotted line here is at 1 is the expectation if there is a standard model Higgs at that mass along that line. Okay. So and then this dotted line here that's dipping around is where what our expected sensitivity is given the amount of data we have and the cleverness of our detector. So where this line crosses it, it tells you, well, here we wouldn't have expected to have seen a Higgs. If it's above about 530 GeV, we wouldn't have expected to see it yet with the data we've got. We're not sensitive to the standard model Higgs at that point. However, we would have expected to see it if it's below that, all the way down to about here, which is about 123 GeV. That whole range, the LHC, should have given us brand new information about the Higgs boson and whether there is one or not. Okay, we could have made that plot without building the LHC. That's the simulation plot. That tells you what we expect. We've done the experiment now, and the experiment is the black line. And you can see that actually we don't exclude the Higgs in this region, and we might have expected to. But the significance isn't great. These bands are 2 sigma. It's not that great, but it's suggestive. Maybe. It may just be statistics. As you go down there, indeed, we do exclude it. We know there's no Higgs over all this range. Maybe here, something. Over all this range, no Higgs. The solid line is below the dotted line. Then here, suddenly, what happens? It shoots up, it goes way higher, and it comes down again. And we didn't even expect to exclude a Higgs here, but we actually have. Even down. It tells you, so you'll learn a lot from this plot. You can go mad looking at these plots if you're not careful. But it's one of the things it tells you is statistics. Beware of statistics. These lines are moving up and down. Every time we make this plot again, everything moves up and down. So you've got to take the errors seriously. Nevertheless, if there was a Higgs, we should have excluded it in this region, and we haven't. And in fact, we see something bordering on suggestive that there might be something going on there, and that's this bump again at about 125. Now, I've been very biased, and I've only shown you the Atlas data. There is another experiment. You should get someone else to talk about the LHC here as well at some point. And they've got results which, in the end, if you put them with ours, say that there's a tiny little window left for the Higgs to be, but there is some evidence that it may be there. Now, scientifically, I would probably not call it evidence because we usually want 3 sigma before we call it evidence, and it's not 3 sigma yet. But we should have, the window isn't as small. The window for the Higgs boson's mass, where it might be, has been shrinking and shrinking, and over the last year, the LHC has wiped out huge amounts of real estate as to where the Higgs might be. But it's stopped shrinking now, and we're in the end game now. We will know very soon. So I've focused on the Higgs. I said, you know, how well the standard model, what we'll learn from the LHC is more than just the Higgs. we'll know when we're learning how well the standard model works above the electroweak symmetry breaking scale. In fact, that's what I do most of my time. I'm not directly working on the Higgs search. I'm working on measuring what happens in proton-proton collisions when we do them at these energies and whether our predictions actually work for a whole range of processes. We will learn why, or something about at least, why the W and the Z have mass and the photon doesn't, where the mass comes from. There are also a whole host of things, new particles that may show up. Supersymmetry is another one which is postulated to explain some of the things that we have up there. Some of the issues that are in that little diagram of particles, the Higgs isn't the whole story. There's other things we'd like to know about it. It's even possible that there are extra new dimensions of space, mini black holes. If those are true, we will start learning something about gravity. I wouldn't bet on it, especially not now, but it's a bit of a long shot. But it is an idea that we're really doing physics in a region where we actually don't know. We're, as I say, essentially doing physics in a fundamentally, qualitatively new regime. It's the region where these two forces look the same, whereas all the physics to date, they don't look anything like each other. And as Rolf Hoyer, Director General of CERN, is a very, very conservative, cautious person, said to the media in October last year, I think by this time next year I'll be able to bring you either the Higgs boson or the message that it doesn't exist. I hope that in this talk I've managed to persuade you that's a very important question to answer. Answering the question is important. It's not finding the Higgs or not that's important. It's not whether the Higgs is a Higgs. It's not like it's a failure if there is a Higgs or a failure if there is no Higgs. It's the fact that this will be crossed off our list of important questions that we need to know the answer to about nature. It's something to do with the electroweak symmetry breaking. So watch out for the next update.